Modern AI models are powerful, but they're bloated, slow, and burn massive amounts of energy.
Neural networks treat learning as a math problem with billions of parameters. That's unnecessary complexity.
We introduce a new AI architecture, simple, energy efficient, and inspired by biology. No layers, no backpropagation, just intelligent behavior emerging from small, autonomous parts. We designed a system that learns and predicts in real time, with no floating point math and no centralized controller.
We started from first principles. Learning should be simple, efficient, and grounded in real-world needs, just like the way nature approached intelligence from the beginning.
500 million years ago, intelligence had one rule: learn fast, spend little, or die. Biological learning doesn't solve equations. It reacts, adapts, and remembers what matters. We took inspiration from evolution and built a system that learns the same way, through observation. That's why, instead of mimicking the brain's wiring, we focused on its function, learning, and prediction. Tech breakthroughs often start with a tiny, elemental component, like the transistor.
Our building block is called the estimator, a device that models a single stream of ones and zeros.
It doesn't count, divide, or compute. It adapts over time, using a few bits and simple logic.
You can look at a crowd like this and just know there are more red shirts than blue. No one's counting, you just see it.
That's the brain function we aim to emulate: fast, intuitive estimation. Not math, not stats. The estimator tells you which signal is more likely, 1 or 0, red or blue.
The breakthrough? Each bit of memory is paired with a random bit. It sounds wrong. Why add randomness when you're trying to remember?
Because we're not trying to memorize, we're trying to form a model, a simpler, faster representation of what was observed.
The randomness ensures fairness, helping us generalize, avoid overfitting, and create efficient models in real time. If the observed value matches a pattern, the model nudges itself, gently shifting over time. If not, it ignores the observation. No overfitting. No noise injection. The model grows only when needed, and naturally converges without complex math. Randomness is built in, not as a bug, but a feature. Just like biology, randomness helps generalize and prevent overfitting. That same randomness also plays a role in prediction, letting us return values that match real-world uncertainty.
The estimator supports two kinds of predictions: the best guess or a probabilistic outcome.
Best guesses are ideal for classification, diagnostics, or identifying the most likely cause. Probabilistic responses are better for creativity, planning, simulation, or predicting what might happen next.
And once you have a component that learns like this, you can scale it into full intelligent systems.
The system is built as a hexagonal grid of identical cells, each one fully autonomous. Each cell stores its own state, handles local signals, and updates itself without instructions.
Cells connect to 6 neighbors, sharing bits of memory and direction with each tick.
No CPU. No scheduler. Intelligence emerges from local interactions. Put them together, and the grid becomes a self-organizing network, capable of learning and inference. Each cell has 3 core subsystems: communication, memory, and connection.
Communication moves pulses across the grid, encoding direction and timing as they travel. And memory detects collisions, moments where 2 wavefronts intersect in space and time.
The connection subsystem builds fast paths between frequently linked signals. Every cell contributes to all three subsystems, and that's where things get interesting. Because now, learning emerges from the behavior of the whole.
Learning begins with wavefronts, slow signals that radiate outward from input points.
When two waves collide, their timing, direction, and values are captured by a collision cell. Each wave encodes how far it has traveled and what it means, without using global coordinates. This is how the system learns correlation, not by data labels, but by collisions in space and time.
Geometry becomes logic. Waves carry history through space.
Learning occurs in parallel across the grid, using only the small required resources to build a connection. At the collision point, the estimator is updated, bit by bit, shaped by experience.
The same circuitry used to learn also makes the prediction. Nothing extra is needed.
Once a collision cell sees a pattern, it can make a prediction before the second input arrives. The location of that cell encodes the timing between signals, midway if simultaneous. If one signal reliably follows another, we don't wait. We predict it early and route that prediction through space to arrive at the right time. The midpoint acts as a timing anchor, receiving predictions exactly when they're needed. Signals that arrive slightly out of sync, like cause and effect, can still be learned and predicted.
This makes the system especially strong for temporal patterns, where timing matters.
It works for video, sound, sensor fusion, anything where sequences unfold over time.
It doesn't just handle temporal noise, it thrives on it. The communication subsystem uses geometry. No headers, no timestamps, just waves. The memory subsystem watches collisions and learns what tends to follow what. The connection subsystem builds and removes fast paths based on predictive accuracy.
Together, the subsystems create an intelligent, adaptive network without hierarchy.
And it works at scale.
Because each operation is lightweight, the architecture is incredibly energy efficient. It doesn't need floating point units, matrix math, or huge power budgets. Everything is done through signal routing and bit manipulation. It's CMOS compatible and massively scalable across large hexagonal grids. Perfect for edge devices, sensors, and anywhere intelligence needs to be low power. It can run inside a camera, a drone, or a microcontroller without needing a data center. And in the data center, it slashes energy costs while maintaining accuracy. The model grows as needed, but only when the data requires it. When relationships fade, prediction paths are pruned. There's no retraining, no resetting, just ongoing, continuous adaptation. It's a general-purpose learning system, just like neural networks, but simpler. Classification, detection, diagnostics. It excels when the goal is choosing the best option. But it also excels in generative tasks, planning, imagining, or responding with probability. This isn't just a new AI model. It's a new architecture. With no controller, no backpropagation, and no heavy calculus, it just learns.
Each cell is simple, but together they predict, adapt, and scale.
This is intelligence without complexity. It's learning, rebuilt from the ground up, on purpose.
We believe this is the foundational technology AI has been missing.
And it's here now, ready to change how the world learns.